Now that we got the mockup running, let's jump to the other side of the fence and set up the server. If you aren't familiar with Spring Boot or MySQL or don't understand why I picked both of them, I suggest checking the previous modules where I discussed the reasons for this extensively and gave a long overview over both. You can create a new database by logging into MySQL and issuing a create database command. I created a new Spring Boot project, which includes Maven dependencies for JPA, which is the Java Persistence Architecture or Hibernate, Jersey, which is the JSON and XML serialization framework, Web, which is useful for web service development, WebSocket for connecting over the newer WebSocket protocol. Security is mostly used for password hashing, which we will discuss. And MySQL support is needed for the JWC connectivity. And finally, Braintree for the payment processing we'll need later on. Before we get into the code, let's take a minute or so to think about the things we need from the server. The first thing the server needs to offer is an ability to add a new user. We also need authentication and authorization for the user, such as password validation and authentication. We need a way to update the user information. We need to track car positions so we can show them on the map. We need the ability to hail a car and pick up a driver. We need to pair the hailed car so the system knows the car is paired to us. We need to log every trip taken, including distance, path, etc. And finally, we need to provide rating facility so we can rate the drivers. I'm glossing over some things here, such as billing, push, etc. Now that we have a Spring Boot project, let's skip ahead to the server code. We'll start with storage, which is a good place to start. A common design strategy is deciding on the data structure and then filling in the blanks. A good way to decide on the elements we need in the user object is through the UI. The account setting class contains a lot of the data we need. The user JPA entity uses an auto increment ID value for simplicity. Let's go over the various pieces here. These are part of the user settings, such as just general configuration. The password stores the hashed value of password and not the plain text version. We'll discuss hashing passwords soon. We will use these when we need to enable login with a social network account. These are the internal network IDs we'll use for verification. A driver is also a user in the system. If this user is a driver, this is marked as true. By referring to both the end user and the driver with the same class, we can simplify the code. If this is a driver, this is the description of his car we'll need for the app. This field is set to true if we are currently in the process of hailing a taxi. If the taxi is taken by a user, this field maps to the user ID. It is set to null if the taxi is available. We will have a separate object dealing with rating, but we can sum it for every query, so the rating value will be cached here. This is the position and direction of the current user, whether it's a taxi or an end user. Notice I chose to just store the location values instead of using one of the custom location-based APIs supported by Hibernate and MySQL. I looked into those APIs and they are very powerful if you need complex location-based APIs. but for most simple purposes like we have here, they are an overkill and would have made the project more complex than it needs to be. If you are building a complex GIS application, I would suggest delving into some of those custom APIs. This is a picture of the user stored in the database blob. One last column is the auth token, which we initialize with a unique random ID. We will use this token to update the user and perform operations only the user is authorized for. Think of authorization as a key to the server. We want to block a different user from sending a request that pretends to be our user. This is possible to do if a hacker sniffs out our network traffic and tries to pretend he's our app. One approach would be sending the password to the server every time, but that means storing and sending a password, which holds risk. In this case, we generate a random and long key that's hard to brute force. We send the key to the client, and it stores that key. From that point on, we have proof that this user is valid. I've discussed this before in the restaurant app if you want to check that out. The repository class for the user starts off pretty standard entries. We first have the option to find a user based on common features you would expect, such as the auth token, phone, etc. However, we also need some more elaborate location-based queries. In this case, I verify that the entry is a driver by always passing true to the driver value. I also use the between keyword to make sure that the entries I find fall between the given latitude, longitude values. The find by driver method finds all the drivers in a region. It's useful to draw the driver on the map even if they are currently busy. The second method returns only the available drivers and is used when hailing. Like before, we need a data access object, or DAO, to abstract the underlying user object and make client-server communication easier. Notice several things about this DAO. First, notice that we don't provide the avatar in the DAO. It doesn't really fit here, as we'll apply it directly to the image. Also notice that the auth token and password are never returned from the server. They are there for the client requests only. In this case, the password would be the actual password and not the hash, as the client doesn't know the hash and the server doesn't store the password. I'll skip the rest of the code as it's pretty obvious, including constructors, setters, and getters. We create the user DAO instances in the server by asking the user object. Notice we have two versions of the method, one of which includes some private information and is useful internally. The other is the one we need to ask for when dealing with client requests. The user service class is a business object that abstracts the user access code. If we think of the user object as the database abstraction and the DAO as a communication abstraction, the service is the actual API of the server. We will later wrap it with a web service call to make that API accessible to the end user. This might seem like an overkill with too many classes, which is a common problem for Java developers. However, in this case, it's justified. By using the service class, I can build unit tests that test the server logic, only without going through the complexities of the web tier. I can also connect some of the common APIs through the WebSocket layer moving forward. So having most of my business logic in this class makes a lot of sense. I have two auto-wired values here. First is the CRUD interface we discussed earlier that I can use to work with users and drivers. The second one is this Spring Boot interface used to hash and salt the passwords. Just using this interface means that even in a case of a hack, your user's passwords would still be safe. I'll discuss this further soon. Adding a user consists of creating a new user object with the DAO and invoking the built-in CRUD save method. Here we encode the password. This is pretty seamless in Spring, but remarkably secure as it uses a salted hash. Passwords aren't encrypted, they are hashed and salted. Encryption is a two-way algorithm. You can encode data and decode it back. Hashing codes the data in such a way that can't be reversed. To verify the password, we need to rehash it and check the hashed strings. Hashing alone isn't enough, as it can be assaulted with various attacks. One of the tricks against hash attacks is salt. The salt is random data that's injected into the hash. An attacker can't distinguish between the salt and hash data, which makes potential attacks much harder. The password hashing algorithm of Spring Boot always produces a 60-character string, which would be pretty hard to crack. I'll soon discuss the process of checking a password for validity, as it's a pretty big subject. Notice that getAvatar uses the ID value that leaves a small security weakness where a user can scan the IDs for images of the driver's users. I'm not too concerned about that issue, so I'm leaving it in place. However, letting a user update the avatar is something that needs a secure token. Continuing with the security aspect, notice that things such as password and token are special cases that we don't want to update using the same flow, as they are pretty sensitive. We have 3 login methods, and they are all technically very similar, so they all delegate to a single login API call. They all throw the user authentication exception, which is a simple subclass of exception. If a user wasn't found in the list, we failed. This should never ever happen, but it's important to test against such conditions, as during a hack these should never happen conditions might occur. Since the passwords are hashed and salted, we can't just compare. Regenerating the hash and comparing that wouldn't work either, as salt is random. The only way to test is to use the matches method. We need to manually set the auth value, as it's not there by default, to prevent a credential leak. The one place where the auth value should exist is in the login process. When we log in, at first, we need to check if the user with the given phone or social network exists. The UI flow for users that exist and don't exist is slightly different. A small piece of the puzzle I skipped before is the security configuration class. In Spring Boot, we can use configuration classes like this instead of XML, which I prefer by far. First, we need to disable some OAuth and CSRF attack protection. Both of these make a lot of sense for web-based JavaScript applications, which are vulnerable to attacks and can use the built-in authentication. But in a native app, they just add complexity and overhead, so they aren't really necessary and can cause problems. If you recall the password encoder from before, this is the location where we include the actual implementation of this encoder. You can place it in any configuration class, but I thought it's fitting to put it into the security configuration class. So far, so good. But the user service is a server-only class. We'd like to expose this functionality to the client code. To do that, we can add a JSON-based web service by using the user web service class. Notice that this is just a thin layer on top of the injected user service class. In the user service class, we throw a user authentication exception when login failed. This code automatically translates an exception of that type to an error DAO object, which returns a different error JSON. Effectively, this means that when this exception type is thrown, a user will receive a forbidden HTTP response with the JSON body containing an error message of invalid password. Maps the user exists with phone number URL, so it will return true or false strings based on whether the user actually exists. Images just map to our URL for the given image ID. So the URL user/avatar/user ID will return the image for the given user with the MIME type image JPEG. If the image isn't there, we'll return an HTTP not found error 404, which we can handle in the client code. The user update avatar auth token API is a MIME multipart upload request, which we can use to upload an image. A multipart upload is encoded using base64 and is the HTTP standard for file upload. We check whether an ID is set to determine if this is an add or an update operation. However, we don't use the ID value for editing them internally, as the underlying API uses the token.